So far, we've seen ways in which our quantitative judgment can be altered from the outside. But what if we just have inherent biases against certain situations? And what if these biases don't line up with math? Let's imagine you're faced with the following choice. Given the following two options, which would you choose? A, receive $940 for sure, or B, have a 95% chance of receiving $1,000 and a 5% chance of receiving $0. Most people would choose option A. We love sure thing. Moreover, we wouldn't make that much more if we won on option B. There's just not that much practical difference between winning $940 and winning $1,000. So why take the chance of winning nothing by opting for B? Well, a very quick calculation shows you that the expected value of option B is $950. This means that on average, picking B leads to better outcomes than picking A. Said another way, our intuition about which option is better does not agree with mathematics. In this situation, we are risk averse. Let's see another example, this time with losses. Given the two options below, which would you choose? A, lose $940 for sure, or B, have a 95% chance of losing $1,000 and a 5% chance of losing $0. Most people would choose option B. Here, we're risk-seeking. But why? Well, most people respond that the loss of $940 is just about as bad as the loss of $1,000. So why not take the gamble and hope that we're in the 5% of outcomes that lose nothing? Well, as in the last prompt, a quick calculation shows us that the expected value of strategy B is a loss of $950. Thus, on average, following option B leads to worse outcomes than following option A. Once again, our intuition about what is best for us does not agree with mathematics. So are we always risk-averse when presented with the possibility of a gain and risk-seeking when presented with the possibility of a loss? If only it were that easy. Let's consider the following two sets of options. In the first, would you rather A, win $6 for sure, or B, have a 5% probability of winning $100 and a 95% chance of winning nothing? In the second set, would you rather A, lose $6 for sure, or B, have a 5% probability of losing $100 and a 95% chance of losing nothing? I think you'll find that your natural inclination led you to option B, a risk-seeking strategy for the first prompt, and option A, a risk-averse strategy for the second prompt. And just as in the previous examples, a quick calculation will show you that both of these options are worse on average. If we thought through all the possibilities, we could come up with the following table. Hopefully by now it's obvious that the way we feel about gains and losses is dependent not only both on the context, both in terms of the probability of successes and failures, but also in terms of the difference in cost and benefit between the safe strategy and the gamble. But these feelings can lead us far astray, especially if we're making these decisions over and over again. In analytics, we often have to define a cost function. This is just a mathematical rule that tells us how much each type of incorrect prediction is likely to cost us. As we've seen, our built-in cost function is not so good all the time. We often overestimate the value of a gain or underestimate the sting of a loss, all for pretty bad reasons. Again, analytics gives us one way to get past some of these errors in our quantitative reasoning.